Hello, Prof. Joe here. This video will be an introduction to kinetics, and it signals our transition to the second half of our dynamics class. So far, we have been studying kinematics. In kinematics, we look at how things are moving, their position, velocity, and acceleration. But now we're switching over to kinetics, where we start looking at why things are moving. Let's jump right in. Kinetics of a particle is where we're going to start. And we're going back to our particle assumption to introduce kinetics. And then we will make it more complicated as we go. So what do we mean by kinetics? We mean why things move. And in general, we're looking at the relationship between forces and acceleration. F equals ma, Newton's second law. And then what about this particle assumption? Well, we are going back to the particle assumption for our intro to kinetics. And then we will learn about how shape and moment of inertia affect kinetics, and then move into rigid body kinetics or planar kinetics, which will be in a couple weeks. So we need to review the laws of motion that we'll be using. You've learned these in physics, but I want to do a quick review of Newton's laws of motion. The first law is that an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by an outside force, or here it says a net external force. That's often called the law of inertia, and we know that objects are going to stay going at constant velocity unless they're acted upon by a force. Newton's second law is the one we'll be using most in kinetics, and that just tells us that the sum of all the forces acting on a body are going to be equal to the mass times acceleration, or the rate of change of momentum of a body over time is directly proportional to the force applied. Finally, Newton's third law: for every action, there's an equal and opposite reaction, which we use when we're drawing free body diagrams to make sure that we have arrows canceling each other out if we separate out components of the free body. So let's use Newton's second law and look at our equations of motion that we're going to use for kinetics. I have Newton's second law listed right up here, and you can see that I have some vector symbols on top because this forces are directional, and so is acceleration. So really, it's the sum of all force vectors is equal to mass times the acceleration vector. We can take that and we can use that in different coordinate systems that we choose to come up with multiple scalar equations of motion. For example, we're going to start out with rectangular coordinates. Rectangular coordinates, we generally, in 2D, will have an x and a y. We have our x and our y axes, and we use unit vectors in those directions, I in the x direction and j in the y direction. And those two vectors we use to do Cartesian vector notation. We are going to do the same thing here with our vector. We're going to say, well, the sum of the forces as a vector is really going to break out into three different equations. The sum of the forces in the x direction is going to be equal to mass times acceleration in the x. The sum of the forces in the y direction will be equal to mass times acceleration in the y. And the sum of the forces in the z direction, if we're in 3D, will be equal to mass times acceleration in the z direction. So we have three scalar equations that came from our one vector equation. And we can use these to solve for acceleration in different directions. Let's move on to an example problem so I can show you how we can use these equations. So first, I'd like to go through the procedure that we'll be using to solve all of our kinematics problems. The very first thing we're going to do is we're going to choose a coordinate system. Now, I just mentioned rectangular coordinate system, but we know that we've also learned about normal, tangential, and cylindrical coordinates. So we'll be going into those equations of motions in the next videos. Once you choose your coordinate system, you're going to draw free body diagrams and kinetic diagrams. Now, free body diagrams you're familiar with. You use those in statics. And a kinetic diagram is just the other side of Newton's second law. If we have the sum of the forces is equal to mass times acceleration, this side we draw a free body diagram for. And this side we draw a kinetic diagram. Okay, let me give you an example. If we had a block and that block had some forces applied to it. Let's say it had a force pulling it down this way. I'll call that F1. We had a force pulling it this way, F2, and then let's say we had its weight pulling it down. And perhaps it's also sitting on something. We have a normal force pushing back up. For your free body diagram, I always recommend drawing the body. Don't draw a point, because we're going to be moving on to rigid body kinetics soon. So it's good practice to draw the body and keep the forces acting where they're acting. Don't move them, because the distance they're acting from the center of mass is going to matter when we move on to our next step. So draw the body, trace the body with your finger, and put a force for everything that's touching it. Even if you think the force is 0, put it on there, and then you can prove later if it's 0. And then also put on a weight, or if there's a magnetic attraction or any other forces that are acting on it. You can see that this corresponds to all the forces acting on that body. Well, we can draw a kinetic diagram for the same exact block. A kinetic diagram is the other side of Newton's second law. And in that diagram, we simply say, where's the center of mass going to be moving? In this case, if this block is sitting on a surface, it's going to slide along the surface. So I would put an arrow here, and instead of marking forces, I'm going to mark the mass times acceleration. So I'd put m(a)x. Kinetic diagrams are always quite simple, and they're just a way of visualizing Newton's second law. They are not drawn based off the forces. They are drawn based off the motion of the center of mass. So this side of Newton's second law. OK, after we have drawn all of our diagrams, including all knowns and unknowns in the problem, we are going to use our equations of motions that I just introduced a few slides ago for rectangular, or whatever coordinate system we chose. We're going to solve for those unknowns until we have the acceleration that we're looking for. However, the problem will not always ask you for only acceleration. So then our kinematics come back. So we've learned kinematics and how to relate acceleration to position and velocity. So if you're asked to solve for another quantity, you'll often need to use your kinematics after you solve for that acceleration to figure out whatever the problem is asking. Sometimes they might ask for how much time it takes to move a certain distance, or maybe they ask for velocity instead of acceleration. Let me give you an example. OK, we have a problem here from the Hibbler text. This is one of my favorite problems because the problem statement is quite silly. Let's read it really quick. The safe S has a weight of 200 pounds supported by the rope and pulley arrangement shown. If the end of the rope is given to a boy who weighs 90 pounds, determine his acceleration if in the confusion he doesn't let go of the rope. OK, I don't see confusion going on in that picture. I see a very irresponsible father saying, here you go, son, lift a safe. And the boy is going to take off into the air. Let's go ahead and set this up. The very first thing we do is we choose a coordinate system. For this one, I think you can see that the safe is going to be moving up and down, and the boy is going to be moving up and down. So we're going to choose our regular rectangular coordinate system. We're going to do x this way and y that way. OK, the next step is to draw our free body diagram or free body diagrams. And actually, even before that, we should write our givens and finds so that we can focus in on this problem and figure out what we need to do. OK, so in this problem, we're giving that the safe has a weight of 200 pounds. I'll put that as weight of safe equals 200. If the end of the rope is given to a boy, the weight of the boy is equal to 90 pounds. Determine his acceleration if he doesn't let go of the rope. And we're also told to neglect the mass of the pulleys and the rope. So we're supposed to find the acceleration of the boy. OK, so now what I want to do is start drawing our free body diagrams. Let's draw the boy first. We have a boy holding a rope, and that rope is going to be pulling the boy up. And there's going to be some tension in that rope, and the boy is going to have some weight pulling down. Now we are in particle kinetics. So even though I drew the tension a little bit to the side and the weight going down, we know that they're actually going to be acting at the center of mass because we're going to neglect the little bit of rotation that would happen when this pulls the boy up. So I'm going to move my tension over just a little bit to make it align with the weight. But notice that I still drew the shape of the boy. The reason I did that is because in future problems, we are going to deal with the rotation. So we got to get used to drawing the bodies and putting the forces on them where they're acting. OK, so we have the tension pulling up, and we have the weight of the boy. So we can say tension equals weight, right? That is what I call statics brain. You're used to looking at a free body diagram like that and perhaps equating those two forces. But that's only the case if there's no motion. We are not in statics anymore. In statics, the sum of the forces equals 0. In dynamics, it doesn't. So we cannot say that the tension is equal to the weight. We have to instead say the sum of the forces in the y direction are going to be equal to mass times acceleration of the boy in the y direction. OK, that's our equation of motion. What are the forces in the y direction? We have t going up. So we have t, we have w going down, minus w is equal to mass of the boy, which is going to be the weight over gravity, which we'd say 90 pounds over 32.2 feet per second squared. Pounds over feet per second squared gives us slugs. Mass should be in slugs, not in pounds, because pounds is a force. And then we have the acceleration of the boy. It can be very tempting to think of those as equal. But now that we're in dynamics, you have to make sure you're using the difference between those two forces to create acceleration. OK, I drew a free body diagram of the boy. Now I'd like to draw one of the safe. OK, the safe, and I'm going to include this top part of it and also the pulley on the safe. And that safe has a weight pulling it down, WS, which is one of the givens. And it has two cables pulling it up. I'm going to call that T and T, but I'm building in one of our assumptions in the problem. They tell us to neglect the mass of the pulleys and the rope. If these are massless, frictionless pulleys, then the tension on one side of the pulley equals the tension on the other side. So we know that the tension throughout the entire rope is going to be equivalent if they are frictionless and massless pulleys. We will be looking at the moment of inertia of a pulley later on, and that would change it so it's not equal. But in this problem, we can say all the tension there is equal. OK, now just to keep track of my equations, I'm going to go ahead and label these two different free body diagrams. This first one down here I'm going to call free body diagram 1. And I'm going to label my equations over here to say that they came from free body diagram 1. And this will just help me keep track of where my equations are coming from. And I'll call this one free body diagram 2. And it looks like I need a little bit more room to write my equations of that. So for free body diagram 2, I'm going to say the sum of the forces in the y direction is equal to mass times acceleration in the y direction. And in this case, it would be acceleration of the safe in the y direction, because that's what's in my free body diagram. And these are for free body diagram number 2. OK, so what do I have in my free body diagram? I have two t's pulling up, and I have one weight of the safe pulling down. And that's equal to mass times acceleration of the safe in the y direction. OK, so now we have a relationship between our tension, our weights, and let's just plug in everything we know so that we can see what our unknowns currently are. So tension I don't know, so I'm going to put 2t. I do know the weight of the safe is 200 pounds. And I know the mass of the safe, because that's going to be 200 pounds over our 32.2 acceleration due to gravity, And then we have the acceleration of the safe. I can drop the y at this case, at this point, because everything is going in the y. But I do know that I have scalar equations, and the only direction that it's moving is in the y direction. OK, so I have one unknown there, the acceleration of the safe. Oh, I'm sorry, I have two unknowns there. I have the acceleration of the safe and tension. Down here, I have t minus 90 is going to be equal to my 90 over my 32.2 times the acceleration of the boy. I have two unknowns there. A total of three unknowns because the t is repeated. But I only have two equations. I have three unknowns and two equations. So now I have to ask myself, is there any other equation that I could get that would relate these variables? This is where we're going to go back to kinematics to find this third relationship. OK, so I put down our two equations we got, one from free body diagram 1, one from free body diagram 2, and we have our three unknowns. And what we want to do now is come up with an equation to relate two of those three unknowns. Well, if we look at the drawing, it looks very similar to some kinematics problems we've done in the past, where we have some pulleys and two particles that are moving. One is the boy and one is the safe. Let's see if we can make a relationship between the motion of these 2 points. So I'm just going to make a quick drawing of it. We've got we'll call that the boy down there. We've got our safe up here. And I'm going to put a datum, a fixed datum at the top. And then I'm going to have my reference distances with an arrow. This would be the position of the boy, and this would be the position of the safe. OK, now what we have to do is come up with an equation for the total length of the rope. You can see that we have two s distances, one here and one here. The other distances are not changing because they're around the edges of the pulley. And then we have a position for B. So we would have the total length of the rope is equal to 2ss plus sb. When we take the derivative of that relationship, the rate of change of the length of the rope is going to be 0 because the rope is staying a consistent length. So we'll say 0 is equal to 2 vs plus vb. And we would say, if I take another derivative, 0 is equal to 2as plus ab. Well, look at that. We just came up with a third equation that is a relationship between as and ab. We can put that over here in our list of equations, and we could solve for, we want to find the acceleration of the boy, so let's solve for as in terms of ab, and we can plug it in. So we would say that 2as equals negative ab, or as equals negative ab over 2. OK. Now we can go ahead and plug that in for our as, and then we'll have two equations and two unknowns. OK, so I'm just going to rearrange things so I can use a matrix. We got t minus 90 over 32.2 AB equals 90 pounds. And then I'm going to have my AS. I'm going to substitute my AB in here. So I'd have 2t minus 200, but it's going to be over 2, and there'll be a negative. So 100 over 32.2 AB is going to be equal to 200 pounds. OK, I can go ahead and solve this using a system of equations where I have the matrix negative 90 over 32.2, 100 over 32.2 times my vector of the variables t, ab is equal to 90 over 200. Okay, augment this matrix with the answer, and didn't need that line there, and do RREF, and we have our answer. And our answer is the tension of the cable is equal to 96.43 pounds, and our acceleration of the boy equals 2.3 feet per second squared. Okay, hopefully that gave you an idea how we can use kinetics along with kinematics to solve these problems. Please let me know if you have any questions.